is Macarena Furque, and I work as a ULO Local Communication and Campus Life Officer at Université Paris-Saclay, and I'm honored to be your moderator for today's Popular Science Lecture. This Popular Science Lecture is part of an ongoing series organized by UGLO, a university alliance that brings together 9 universities from across Europe. The series aims to provide accessible interpretations of science for a general audience. Today, Université Paris-Saclay takes the lead in hosting the lecture on the intriguing topic of the dark side of the universe. The goal of this series is to make scientific concepts understandable and engaging to everyone, regardless of their backgrounds in science. It's a fantastic opportunity to bridge the gap between complex scientific ideas and the broader community. Attendance will gain valuable insights into the rich history of the universe through a dynamic interplay of theoretical concepts and observational data. Additionally, you will have access to captivating images captured during recent space missions. The immersive experience will not only offer a visual journey through the cosmos, but also provide you with the opportunity to engage in insightful discussions by asking your questions in the chat that will be answered at the end of the presentation by our panelists. I will now introduce our speaker, Professor Hervé Dole. Professor Hervé Dole is a professor of astrophysics working at the Space Astrophysics Institute and Vice President for Arts, Culture, Science, and Society at Université Paris-Saclay. As scientist, he's a specialist of galaxy clusters in the early universe and the infrared radiation as seen from space. He's involved in European space missions, Euclid, Planck, and NASA space missions such as James Webb Space Telescope and Spitzer. As University Vice President, he promotes the arts and culture at the university for students and colleagues, helps foster prestigious partnerships with, for example, the Centre Pompidou, Louvre, and Villa Medici, and builds stronger relations between science and society, especially with schools, citizens, and media. Professor Hervé Dole, the floor is yours.
Thanks, Macarena and Isabel, who is in the background. Thanks for UGLO for inviting me. I hope you hear me well. I'm going to share my screen, and indeed, I'm going to talk about the dark side of the universe. I will show you latest results of what we basically don't understand in the universe, which are many things. So first, let's share it, and then let's start it. Voilà. You should see my slide about with the title and a nice image from the Euclid European Space Mission in the background. Dark side of the universe. So I wanted to split my talk in 5 sections. First, an introduction about what we're going to talk. Second, a short word about science and society. It will be on 2 slides. Then we'll take a tour of the universe from the solar system up to almost the Big Bang. And then in section 4, I'll express how can we see something that we cannot see, namely dark matter and dark energy. And then I'll show you the first results of the Euclid European Space Mission, in which many colleagues are involved here in Paris-Saclay, but also in other UGLO university and across the continent. And you can ask questions in the chat, apparently, so that's please leave your message there. So a long time ago in a galaxy far, far away, you may remember those words from some movies. Actually, we are trying to understand the origin of the universe scientifically, because you can do that artistically or with other means. But here we're talking about science. And in order to achieve this goal of understanding the universe, we do images like this. This is an image from the JWST, James Webb Space Telescope, cooperation from NASA, CSA, and ESA, so basically the US, Canada, and Europe, where we built important instruments. And you see on this image a few stars from our own Milky Way, but mainly galaxies that are far, far away. Some of them are at the edge of the visible universe. If we make a zoom on these two red dots on the bottom right, these are two galaxies that we discovered with colleagues from Marseille and across Europe and the US. These galaxies are emit their light a few hundred thousand years after the Big Bang. And we discovered them, and this is one of the first, what we call galaxy protoclusters, one of the first structure that collapsed in the early universe, and we're really excited to discover it and to study it. I put some numbers, and we can discuss later if you want, because the numbers are astronomical, basically. So these galaxies are far away. These are far from being the record. The record is much higher, but still it's significant. And also a nice thing to see on this image, I don't know if you can see my, no, apparently not, my mouse. Maybe I have an option to do that. No. Pointer options, laser. Let's put a laser, a red laser. Does it work? No, it doesn't work. Too bad. So on the top left of the image, you see curiously shaped galaxies. They look like elongated and curved. Actually, they are not like this. They are regular galaxies, but the light coming through the galaxy cluster is deformed, is changed because of the presence of dark matter. I'll come to that in a few moments. So to start with, I like to remember that physics is everywhere in the world. I won't detail the equation because that was not the idea today, but the idea is to highlight the fact that Galileo Galilei in the 17th century, that's the right image, first understood the way the pendulum worked. Then the middle image on C, it was done in the science fair here at the university, where my colleagues put me into a giant bubble, and the bubble vibrates. You may have done that in your garden with small stuff with bubbles, and the bubbles vibrate, and the equation of their vibration is written on the bottom. And it's the same form of the pendulum by Galilei. And if you look on the left, the image B is the sun nearby us, and the sun is a star, and this star is vibrating also. And the equation of its vibration is written on the bottom left. But without being a specialist, you may see that the form of this equation is exactly the same as the bubble or the pendulum. And the first image on the top left, labeled A, is the image of the whole universe just after the Big Bang. It's called the cosmic microwave background. It's the first light of the universe. And at that time, almost 400,000 years after the Big Bang, redshift 1000, the universe was also vibrating. And this vibration follow also the same kind of equation. So what's nice about physics is that we are able to explain whenever we can natural phenomena with the same kind of equation. And that's the unity of physics and the beauty of physics, at least to my mind. And our goal is to understand the structure, the evolution of the universe and its constituents, and the fundamental laws like gravitation and things like that. It doesn't mean that we understand everything. You'll see in a minute that we have no idea about what dark matter and dark energy is, but still, the few things we understand, it's pretty cool. Wonders are everywhere too in the universe. When you look at these kind of images taken from the JWST, on the left is our own Milky Way nebula within our own Milky Way, and on the right it's 5 galaxies much further away. You see that these wonders are make us wonder what the universe is made of, what is its history, and why is it cool to observe it? Because it's beautiful too. So of course there are colors, but it's very nice. So wonders are everywhere. Questions are everywhere too in the universe. We try to understand where the universe come from. The image in the middle, the colored image, is the cosmic microwave background. So the first light of the universe just after the Big Bang. And we realized that the universe was really homogeneous at that time. And we don't understand why. We would expect more differences there. And so there are questions like why the early universe just after the Big Bang, was so homogeneous because we wouldn't expect it. And so to understand that, we, the colleagues, the scientific community developed a model which is called cosmic inflation that is able to explain what we observe. I won't come into the details, but it's to give you an idea. And then another question on the bottom right is the universe was homogeneous. That means from any direction you could see the same thing roughly. Now we see a very heterogeneous universe. You have big galaxies with a lot of matter inside, and outside galaxies, in the holes, in the vacuum, there is almost nothing. This means that the universe is structured. There is big stuff somewhere and nothing elsewhere. And again, we are not sure to understand why it is in such a way, because gravitation alone has trouble to explain all these things. And so we came to realize that if we add dark matter, which is an enigmatic matter that we don't see, but we can measure the presence, it helps us explaining why we do see galaxies and why they are there. And also dark energy, I'll come to that later, explains the expansion of the universe. Explain is maybe it's too strong, at least describes the accelerated expansion of the universe. Questions are also forever. I'm not an historian, unfortunately. I would love to do many other things, but I can't. So I took a few images here and there from various cultures, mainly the Renaissance or earlier, so from the Muslim world or the Christian world. And every civilization has its own way to understand or describe the universe. At that time, the universe was geocentric, so the Earth was in the middle. And so it's also a poke to our colleagues from Porto, because there are documents from Portugal and elsewhere in Europe. And also it's beautiful images from the Renaissance or the Middle Ages. And what I like the most on this slide is the top right image which is black and white, which is on the second 12th century, which is the description of the composition of the universe, the four elements: air, water, fire, earth. It was a good times to be scientist there, because you have only 4 components and you could explain everything. That was a cool time being a scientist. Now it's more complicated, but I wish I lived in those times. It was easier. Anyway, so that was their way of understanding the universe. I mean, it's no way to make fun of them, because it's different context. So, but they had good success in predicting a few things. But it's to mention that since humanity is humanity, we have questions. And now I'll go to astrophysics. But before astrophysics, I'd just like to make a word about science and society. In these days, especially in Europe, but not only in Europe, in many continents, we hear many, politicians or whatever people that express many opinions, which is okay. But sometimes we wonder where they speak from. And so I like this drawing from Tom Gault for the New Scientist last year, where he expresses with nice colors the fact that we all know something, but also there are zones when you go outside your area of expertise where you can see completely stupid things and you are completely ignorant. And so it's, as a scientist and academics, it's everyday work for us to make sure that when we speak, we are in the yellow zone. And if we happen to be in the external zone, then it's not as a scientist that we speak, it's just as a regular citizen. And I guess everybody in the media should do the same. Apparently, it's not the case. And a few months ago, I provided a small article in a French newspaper stating that scientific culture should be part of the general culture, especially in the governments and the economy, which is not always the case. It's sometimes the case, but not always. And maybe we should have more rational treatment of public affairs. And the UNESCO, so United Nations, in their recommendation for scientists, a few years ago, they provided 10 points. And the point number 2 is science and society. So I encourage people to do more connection between science and society. And they define science and society in the following way. It's the bottom left blue panel. The need for science to meaningfully interact with science, with society, and vice versa. It's not one way, it's 2 ways. So I hope that today we participate to science and society by providing meaningful interaction, and we will value your question and discussion at the end of the talk. So coming back to cosmology, let's start with a short tour of the universe. So ready to make billion light years of travel in 4 minutes. So we'll start with the solar system. So everything I'm showing is real images from our space missions or telescopes. So let's start with the solar system. So you may recognize on the top right the Saturn rings, seen from Cassini space mission. Beautiful. So we went there with robots and telescopes. That's super cool. On the bottom left, you see the biggest planet of our solar system, which is Jupiter, with the big red spot, which is a big cyclone. On the top right, I guess it's Neptune. I forgot. I guess it's Neptune, seen from University. So Neptune is the last big planet of our solar system. You may know that there are dwarf planets like Pluto or Ceres. They are still belonging to the solar system, but they are minor planets. And on the bottom right, you see a landscape from Mars, the planet Mars, where so far, I guess, only US and Chinese spacecraft were able to land safely. And this image is taken from a French-US camera, because the French provided some part of the camera. So it's an amazing playground to discover and send the instrument to understand how the system solaire was formed, and that's pretty exciting. I also like this image. It's not my vacation of last summer. It's a sunset from the planet Mars. So sunset from Mars, taken a few years ago by Spirit. And you could see that it looks like the Earth sunset, but slightly different. The sunset is blue, and the temperature and pressure is different, but it looks as beautiful as on Earth. Also, to put in perspective what we are doing every day, this is us. The small dot in the middle of the screen is the Earth as seen from Mars, again, a few years ago by Spirit. So the Earth is the only planet we have, and there is no planet B. So we should preserve it, because there is no way we could live as humanity elsewhere. We could send a few people, if possible, not only rich people and stuff like that, but we could send a few astronauts somewhere for a few months, years, but the whole humanity, there is no other option. So we should value what we have here and protect it. A few real solar system landscapes. So when I have time with my students, or when I do conferences, I make people vote. What do they see? What are the landscapes? But today is more, we have less time, so I'll go through it. So from left to right, the leftmost image, which is yellowish, is the surface of Venus. Venus is a nice planet. Unfortunately, the pressure is so high that it's like 100 times more pressure than on the Earth. The temperature is something like 480 degrees Celsius. So it's really hell on the solar system. Then the next image is the Earth. The third image is the Moon, Moon, and with the Earthrise. The fourth image, the red one, is the Mars surface. The image labeled 4, but it's a mismatch of the numbers, sorry. So the orange image is taken from a European space mission. It's the surface of Titan. Titan is the major satellite of Saturn, and Europe landed there in 2005. It's something like minus 200 degrees Celsius. And there are rivers there. Of course, it's not rivers of water, because water is freezing at 0 degree. as you may know. So minus 200 degrees is not rivers of water, it's rivers of methane, CH4, methane. So the methane there is liquid, and so you have rivers of methane. And then on the right is the comet. It's a picture actually from Orsay, from my lab, with connection with other labs, of course, with the European Space Agency. But it's the comet Churyumov-Gerasimenko. You may have heard it. It's the Chury comet back in 2014, when the European mission Rosetta and Philae landed on this comet, and we could see the surface of this cometary body. It was super nice adventure. Now we leave the solar system, we go to a much higher scale, at the scale of light years from here. And we see stars. These are images from the Hubble Space Telescope. We see that stars have different colors, different temperature, different masses. There's a lot of stuff about stars, and they are pretty cool. Their temperature ranges from 3,000 degrees up to 15,000, something like that, which changes their color. And one of the stars is ours. It's the sun, 8-minute light from us. And the stars we are seeing on the picture are something like maybe 100 of light years from us. We go at a larger distance. We are still in our own Milky Way, and we have nebulae. Nebulae in our own Milky Way is just gas. Gas is just particles, hydrogen, silicon, magnesium, carbon, oxygen, I mean, whatever the star produced within the billion years. And these clouds, these nebula, sometimes collapse, and they form stars at the end. These are the red zones where the new stars are being formed, and it's pretty cool pictures. And this is what we call the interstellar medium within our own Milky Way. If we go much further away, we can see other galaxies. So the images you are seeing are external galaxies, and their distance ranges from 2 million light years to a few billion light years. And so the size, the diameter of each galaxy is something like 100,000 light years. So it's a big stuff. And almost a century ago, we discovered that there was a problem with this galaxy. So galaxies mainly stars and dust and nebula, as we just saw in our own galaxy a few pictures previously. People realized that, they look like they rotate. They were able to measure the speed, and they realized that they rotate too fast compared to the mass that we see. It's like so there was a discrepancy. Either we don't measure right the speed of the stars that rotate around the galaxy, or we don't measure well the mass. We choose the second solution for various reasons, and we realized that we need 10 times more mass than what we see in order to explain the speed of rotation of the external stars on these galaxies. It's a big factor, 10. It's not 5%, 10%, it's times 10. We miss 10 times of the mass. And we still don't know why today, even 100 years after, we don't know. So the idea is that there is a hidden mass that we call dark matter. There should be a hidden mass that we don't see, but that is there, and that explains the form of the galaxies. Well, you may say, well, that's easy. I mean, you don't understand, so you invent a new mass and stuff. But we tried everything else we could, and it didn't work. It doesn't mean we're right, but given current knowledge, scientific knowledge, up to this day, we have that's the best solution in a way. Another solution could be to change the theory, because if we change the gravitation theory, we could have different explanation. And people are working on that too. But currently, these alternative theory are not at the level of maturity as the general relativity, which works pretty well. So it doesn't mean it's not the good solution. It just means that it's maybe too early for these new theories. So let me give you an analogy. You may be in an office right now, or at home, or in a car, or whatever. So you are breathing the air around you, otherwise you would be dead. So you are breathing the air. And did you ever see a particle of air with your own eyes? I mean, the oxygen and nitrogen that is present around us that we breathe, I suspect you never saw any particle. So it is possible to have non-visible particles, but we see the effect. We breathe them. We can measure the density and the pressure of the air around us, but we don't see the particles with our own eyes. So we think dark matter is the same. We cannot see it currently with our current technology and knowledge, but we see the effects and we can measure the density and the pressure on these galaxies. I won't go into the details, obviously, but we have ways to measure it. So that's why we think dark matter is there, but there are still problems. So it's part of the dark side of the universe because we think it's there, but we don't see it. I'm going through these images. And we have also galaxy clusters. So galaxy clusters is a bunch of thousands of galaxies. So the images I'm showing you there have physical size of about 2 or 3 million light years across. And you have something like 3,000 galaxies in each image. And the mass of those two guys, those two galaxy clusters, is around 10 to the 14 solar masses. That's the unit we use. So galaxy clusters are the biggest stuff of the universe, biggest gravitationally bound structures, and we study them because it's really interesting. And then we go to the edge of the universe. The edge of the universe, we call it the horizon, cosmological horizon, is the further away things we can see, and this is the cosmic microwave background, the first light of the universe, or the fossil record of the Big Bang. This is a light that was released in the universe something like 400,000 years after the Big Bang. And that we see today, it's complicated. We saw that with the Planck satellite, the European space mission that did that a few years ago. I was happy to participate to this adventure. And what we see is the small color, it's false color because it's a cold light. About 3 Kelvin. For those who know science, it's only 2.7 Kelvin black body radiation in the universe. And the small colored dots represent a small variations of density, small fluctuation of density. So there are little bumps up and down, little bumps up and down of matter. But the difference between the up and down is really small. You know, it's 300 microkelvin, so one of the millions of Kelvin, which can be translated into very small fluctuation. That's why we observe that the universe is very homogeneous because we choose the scale to show it. And the gray line in the middle shows the location where it was very difficult to observe because of the Milky Way and some galaxies. So this is the story of the universe. Well, not the story, but the scale of the universe. We went from the solar system up to the first light. And the history of the universe can be summarized as the following. So again, the history of the universe in 30 seconds. We start from left and we go to the right. From left, we start with the Big Bang, which is singularity, and the expansion is incredibly high. Then we have the cosmic inflation that lasts for something like 10 to the minus 32 seconds. And then the universe is still very hot and very dense. So you have the synthesis of the electrons, protons, dark matter, everything. And then, so I'm going quick, you see the colored bar, which is the cosmic microwave background that we just saw, 380,000 years. This is the moment, the epoch where the light could travel freely in the universe. That's why we observe it now, and before it's not possible. And then you have the matter that is possible, the matter is allowed to collapse through gravitational forces and then create galaxies, galaxy clusters, stars, planets, and eventually life that we know today on Earth. And this takes about 13.79 billion years, despite what's written. And so something like almost 14 billion years to do. So the universe, we know the universe is very old, and we have a clean measure of it. I won't show many numbers, but I will show these. This number, of course, we won't go through it to them individually, is the universe identity card with basically what is the universe we're living in. This comes from the Planck mission, European Space Mission that we did a few years ago. On the red box, you can see the age of the universe, 13.79 giga year, so a billion years, if I'm right, and with a high accuracy. It's the first time in the history of humanity that we are able to measure so precisely the age of the universe, given a cosmological model. And among all those strange numbers and notation, I highlight two with arrows. One is omega C on the top, and omega C means C for cold dark matter. It means dark matter. It means that we need dark matter to understand the present universe. And there is a number associated to it that we measure. And on the bottom, I mean, in the middle, you have omega lambda, and lambda describes the dark energy. The dark energy is a simple way to describe that the expansion of the universe is accelerating. It's not something that we want, it's something that we observe. So we have to take into account the facts that we observe, even if we don't like it. So the universe is expanding at an accelerated rate. We have no idea why, but I mean, that's what we observe. So in order to I was going to say to explain, but it's not to explain, to describe this accelerated expansion, a natural way to describe it is to add a strange energy. So it has nothing to do with matter. It's a strange energy that provokes the accelerated expansion of the universe. And if you use this hypothesis, it works pretty well. It works actually amazingly well. We have these numbers that comes to an incredible accuracy, and that works fantastically well. So this is the dark side of the universe. I guess that's, yeah. If the universe is today composed of ordinary matter, 5% in yellow on the left. Ordinary matter is you and me and the trees and planets and stars and things like that. Then we have something like a quarter of dark matter in blue in the cosmic pie. I call it cosmic camembert because I'm French, but we call it cosmic pie. And then on purple, its dark energy is something like 70%. But I usually have the question, well, what about, you know, my office or my country or my whatever? I don't see dark matter and dark energy. I see everything. And you're right. In the solar system, we have 100% of ordinary matter. So there is no strange stuff. It's regular matter. It's only when you go to billion light years scale that dark matter and dark energy takes over. So in our own human daily life, we have only ordinary matter, and that's fine. So this cosmic pie, this cosmic camembert, is only valid at the whole scale of the universe. So this is a big change from what we had in the 12th century, where we had only, you know, air, water, fire, and earth as composition of the universe. They had 4 elements. Now we have 3 elements, so we make progress. The problem is that the 3 elements, we only know 5% of the total. Of course, it's a joke. It's more complex than that. We know better the structure of the matter, electrons, protons, atoms, molecules, energy, everything. So we understand better the constituent of our own solar system. But still, there are questions of why we don't understand dark matter and dark energy, and basically why we don't understand this dark side of the universe. And I like some memes I'm showing to my students. So each time there is a problem in physics, there's always either dark matter, dark energy. And to explain dark matter, I mean, it has to be a matter that is sensitive to gravitation. Sometimes theoretical colleagues or particle physicist colleagues invoke exotic matter. So these are the 3 usual suspects in physics. So if the universe was a pizza, I hope you're not too hungry, that you had lunch already. If the universe was a pizza, like this picture, this is what we can see. You could only see the olives, which is the ordinary matter, which is fine if you know only the olives. The problem is that we feel there is the pizza around us. We feel the mass, we feel the smell, we feel everything. So that's really frustrating. Because if we were ignorant just to see the olives, that would be nice. We thought, we could think we know the entire universe, and that's fine. There's just olives, it's good, olives are good, right? So the problem is that we know there are good olives and we like olives, but we know there is a pizza around it, but we cannot see it and we cannot take it. So that's annoying. So that's why scientists, astrophysicists, and physicists are excited and frustrated at the same time, because we want to eat the pizza, but we can only see and get the olives. So that's the summary of the dark side of the universe, because everything is tasty and look good, but we have access only to 5% of it. So how do we see dark matter and dark energy? I will be brief on that. We have friends that are galaxies. Galaxies allow us to highlight where dark matter and dark energy is. And I have two things to show, on the left and the right. On the left, galaxies trace the mass present of the dark matter. I mean, the mass is composed of dark matter and ordinary matter. And galaxies have a good property of letting us know where the mass is through galaxy clusters, for instance, and through gravitational lensing. I will show a picture in next slide. That's for dark matter and mass on the left. On the right, we want to measure the expansion rate of the universe, because dark energy is involved in the rate of expansion of the universe. So what we do, we measure the distance and the speed of faraway galaxies, as highlighted in the drawing, in the plot on the right side. The more further away the galaxy is, the more red it becomes, and so that's why going to the infrared is interesting. So for dark matter, we are looking at the mass and the position of galaxies, and for dark energy, we are looking at the speed and the motion and the distribution, spatial distribution of the galaxies. So how work mass? Dark matter is acting like a wine of glass. You see the picture on the left. If you put a lens like a wine of glass, a glass of wine, sorry, it's better in the right order, a glass of wine, you see that the background image is distorted. It acts like a lens. Einstein, like a century ago, was the first to understand this effect, and we see it now. It's called gravitational lensing. So on the right image, you have a real image of a galaxy cluster, where you have dark matter that we don't see, but the dark matter introduces a perturbation in the images of background galaxies. You may see the galaxies that look like shaped and with strange forms. Usually galaxies are straight and they are not shaped, curved shape like this. And this is an effect of the gravity that is present in these galaxy clusters, and we can measure the exact quantity of dark matter in this cluster thanks to this effect of distorting the images. If you prefer, it's like a surface of a swimming pool. So dark matter would be the surface of the water, but you only see the bottom of the swimming pool. And you see with this structure that I guess you're all familiar with, you see that something happens at the surface of the swimming pool. It's the same. The light is perturbed, is shaped, so that at the end you have this nice feature on the bottom of the swimming pool. Here it's not mass, it's not dark matter that perturbates the light. It's just the waves on the surface of the swimming pool, but the effect is the same. If you in the universe you put a big bunch of dark matter, the light is distorted exactly like this. So either you prefer a swimming pool, or either you prefer wine, or you prefer both. But that's the effect of dark matter on galaxies. And for expansion of the universe, we use galaxies as a flower on the pizza dough. On the pizza dough, when you, I'm not a pizzaiolo, but you've seen the image. If you rotate your pizza dough before going to the oven, you expand your pizza a little bit, but the particles of flour are not expanded themselves. They are just in the pizza dough. So galaxies are the same. Galaxies don't expand themselves, they stay the same, but they are taken away with the flow of expansion of the universe. So what we do, basically we measure the particle of flour in the pizza. That's what we do to measure the expansion rate of the universe. We measure the speed of the galaxies that are going further away. And to do so, we go in the infrared. So I'm showing you one, two, three, four picture, I guess, in the visible light. So on the top left is 3 bottles, which is called, and so you can drink with your friends for the aperitif or not. In the middle, it's my students at some observatory. On the right, it's my colleague, Dr. Henry Joy McCracken, with a coffee. So is his coffee hot or not? And on the bottom, you will discover what it is. If you use an infrared camera, like we use infrared to see further away galaxy, you will see a new reality. And this is this reality. I'm going to blink while I'm speaking. So on the top left, the bottles, you see that the leftmost bottle is hot because it's bright in the infrared, while the 2 bottles on the right are cold, so you can drink them unless you like hot champagne, but we won't be friends then. Then my students in the middle, on top middle, you see that they are good students because their head is hot. That means they are thinking hard about what we were asking them, sorry. So voila. And on the right, my colleagues, Henry, has a hot cup of coffee because you see it's bright in the infrared. And on the bottom, you see that it was a picture taken at night with my students, that there are 1, 2, 3, 4, 5, 6, 7 students that were hidden at night and we could see in the infrared. So it's an idea to give you the idea that going to the infrared is interesting to observe other things. And to do so, we designed a new space mission, which is amazing. It's called Euclid. We launched it last year. It's working beautifully. I will show you the first results, the first images, and then I will stop. This is the image just before launch, when it was taken at Thales Aliena Space in Cannes, south of France. It's a big stuff, you know, something like 2 tons, 4-meter high, big telescope, amazing cameras, highly sensitive, the biggest camera we ever sent into space to observe galaxies. And it's pretty cool. And this was an image I was taken in the clean room before sending it to the launch. I'm skipping that. So this is the first images of Euclid with the 600 million pixels camera. We see stars, we see galaxies. So this was the first image of the visible camera, and this was the first image by the infrared camera, and we put red colors to change it. So it worked beautifully. It was fantastic. But then the second image was this one. We had a problem. The second image was not as good as we anticipated. Basically, the space telescope, Euclid, had a problem of finding its way through the stars. He was lost between the stars, so he started to basically to jingle around because he could not stay fixed compared to stars, and he started to rotate and to find his way. And that's why the stars are completely, you know, doing these funny shapes. But we eventually fixed the problem with the industry and with the scientists. And so now everything is working beautifully. And you see the effect. This is before Euclid, and this is after Euclid. So before, after, before, after. Even though you see strange lines, we could discuss it. It's effect of cosmic rays. So we still are working on it. Again, before Euclid on the ground and after Euclid in space, you see there is some improvement. And then we released, and I'll finish on these 4 or 5 images. We released amazing first results few weeks ago, and I'm going to show you. Euclid is well, I forgot to mention that Euclid will measure the presence of dark matter and dark energy through the effect of gravitational lensing on one way and expansion rate and correlation of galaxy in the other way. But first, we have to make good images to make sure it's working well. And so this nice image of the Horsehead Nebula in just 1 hour observation tells us that Euclid is working perfectly well. And Euclid has a huge field of view, the largest field of view that any space mission had ever flown. We have also a nice image from a cluster of stars in our own Milky Way. You can see the sharpness of the images. We are close to the Hubble Space Telescope sharpness of the images. It's really amazing. Then we have a faint galaxy. It's nearby to us, to our own Milky Way, but it's very difficult to observe. But Euclid, in just 1 hour could get it. So it's really fantastic. And one of my favorite images is this galaxy, spiral galaxy. You could see all the colors, you could see everything, ultra sharpness of the images. These images are public. You can Google Euclid images, you can download them at high resolution. And actually, this is my favorite image from my colleagues, Jean-Charles Cuyandre, Paris-Saclay. This is a galaxy cluster, nearby galaxy cluster, and all what you see is galaxies all over the place. The biggest one are nearby, and the small dots in the background are a faraway galaxy. And to give you a perspective, the Hubble Space Telescope in 20 years of operation could observe only those square on the images. I'm not saying that the Hubble Space Telescope is bad. Of course, it's an amazing telescope. But he observed on very tiny pieces of the sky. And Euclid, in one shot, observed all this scene, all this big field of view. So this is a major achievement for European science. We have the US colleagues on board too, indeed. And then I'll finish up with a short video showing you the richness of the Euclid data. In Paris-Saclay, we have a big screen. I guess in every university you have that. And even a big screen is not enough to look at the Euclid data. So we have to zoom them on a screen that has the size of a complete room. I'm showing it again, and then I guess I'm done. So if you have a big screen or even a small screen, you can enjoy those images. And the first science results of Euclid are expected in a few years from now, because we need a lot of statistics and we need a lot of processing to go into the dark matter and dark energy. So stay tuned. And to conclude, Euclid, the mathematician, 24 centuries apart, and Euclid, the European Space Mission, share the same goal, better measuring the universe and better understand the universe with the help of science. Thank you for your attention.
Thank you so much, Professor Hervé Dole, for this very interesting perspective on the history and the content of the universe. We have already some questions on the chat, but I would encourage the audience also to type the questions on the chat, so you can answer them. But we have already 10, so I think it's a good number. I'm going to start with the first one. So we have one person that asked, maybe a little off topic, but do physicists agree on why the Big Bang happened?
Yeah, it's a tough question. We have models, so every scientist agree that the Big Bang happened first, because it's the best model we have. It doesn't mean that it's the truth. It doesn't mean that it's the best theory, but that's the only one we have. Actually, the Big Bang is more a collection of theoretical parts that plug together and that we are able to predict what we observe, that we had observed and new observations. So the Big Bang is really a consensus. Why did it happen? Colleagues have some explanation. I'm not an expert on that, but if you have quantum fluctuations in early vacuum, then you could explain why the Big Bang happened, and actually you could have different universe not connected. Science fiction can do things, but science cannot. So you can have different universe, multiverse, that are completely independent, and one of them is ours. So I guess it's still a work in progress.
Thank you very much for your answer, Professor. And the second question is how society can contribute to scientific research in practical terms?
Yep, I guess we could spend hours on that, but to make it short, I guess two ways. One way, which is top-down, so it's to participate to citizen science or participatory science that scientists propose, like measuring birds, flowers, galaxies. There is a galaxy zoo that you can participate on, and every participatory science that exists, even particle physicists, you can analyze stuff on your computer, or that's the first thing. And the second thing is bottom up, is to meet colleagues or scientific, academic colleagues or associations to help bringing new topics like agriculture, biodiversity, cars in the city, more societal problems where science has a good can bring a good light, but not only science. I mean, citizens have have experience and right to say their own opinion, of course, and politicians and association too. So you can connect to consortia, to associations, to people, to bring new topics on the table, and then universities can bring a few, and then you can collaborate with that. Each on its own respect, but it's possible to do that too. It depends if it's about the cities, about natural science and everything.
Thank you. Another participant also asks, you mentioned that it's important to have experts talking about science. What do you think about the trend with Hollywood movies that talk a lot about science, such as Interstellar or Constellation, which both explore the possibility of the existence of several dimensions in the universe at once? Are they making science trendy, or are they spreading misinformation?
I guess none of them. I guess it's great that art or creativity or movies, even if it's an industry or whatever, it's great that they don't pretend to do science first, and I guess they don't. So that's good. So it's clearly separated. We separate science and movies and whatever. It's true that science is part of those movies because usually they are very well done. Also, Don't Look Up and things like that. They are very well done, and they have a real science background. But their purpose is to make us dream or make us react or whatever. And then it's fiction, so then they do whatever they want. And I guess it's good because sometimes ourselves we don't dream too far. So I don't see a problem of books, movies, music, whatever, exploring things that scientists don't know necessarily. And I guess it's good that creativity can be inspired by science. So that's pretty cool. As long as they don't pretend doing science, right? As long as it's clear. So I'm perfectly fine with that. So that's why I said that they don't spread misinformation because it's just fiction. And about several dimensions, theorists predict that universe may have 11 dimensions or so. So it depends what scale in the universe you are looking at, what phenomenon you are looking at. Cosmic strings are different than dark matter. So multi dimensions are existing in theoretical physics. So that's a fact. But can we see it in nature? That's still the debate, scientific debate, because sometimes you can explain things that you see, sometimes not. So I'm not shocked by that. And is it trendy? It depends. I guess the general public might be captivated by things in science that are not maybe trendy in science, and that's good. I mean, if we all go in the same direction, maybe that's sad. So if the general public is interested or captivated by multi-dimension stuff while it's not a hot topic in science, I'm perfectly fine with that. Again, as long as we don't pretend that it's science in the movies or whatever. So no, I guess it's good that science fiction or social movies or whatever sometimes take a lot of liberty with science. I guess it's good.
Thank you, Professor. We have 4 more minutes, so I'm gonna read, I think, 3 more questions, since we have to wrap up at 14th. So the 4th question would be, do you think it would be possible at some point for the human population to live on another planet if the Earth gets inhabitable due to climate change?
No, as I mentioned, there is no planet B. So to the current knowledge, there is no way a large fraction of humanity could go elsewhere. You can send, 10 astronauts somewhere in Mars, on the Mars planet, that live for 2 years. We don't know yet doing that, but I suspect technology will improve. So you can explore, that's no problem. But bringing all humanity, there's just no question. Scientists agree that the fact that the Earth ecosystem is unique, at least for us, it's completely unique, and there is no way we can escape it. So we better preserve it. And it's funny because people are asking the question of, going into space. People are never asking the question, why wouldn't we live in the oceans, in the bottom of the oceans? Because we feel that living in bottom of the oceans is just impossible. But we may think because of Elon Musk's stupidity or whatever, that space is accessible, but it's even worse than the bottom of the ocean. So there is no way. Again, we can send a few humans for a few weeks, months, years maybe. But the whole humanity is just impossible, at least to current knowledge. So we better preserve what we have.
Thank you very much, Professor. We have one more question that we might answer. What would you suggest that the median of the universe itself has no zero core in a particular shape that would lead to consistent over-rotation across all galaxies? Well, this is a hard word maybe to answer in 1 minute.
Let's see, which question is this?
If not, we can also, since we are running out of time, I can send the questions to you and then I can address the answers to.
Yeah. I see one question, which is the black hole. That's, a black hole is ordinary matter. It's just a collapsed ordinary matter. So that's why we call it black and not dark. You can see the subtle difference. And yeah, I could answer to the other questions, and maybe you can send back to the.
Absolutely. I'm gonna collect all the questions and I'm gonna send the answer to the participants. This lectures has been recorded, so you will get also the link to access the recording of this lecture. So it's time to wrap up. I would like to thank you, the audience, for the participation, the activity, and relevant questions. Would also like to thank our panelists, Professor Hervé Dole, for this amazing presentation and the dedicated work to the research field of astrophysics and the topic of the history of the universe. And yeah, I welcome all of you to join our upcoming UGLO Popular Science lectures. Thank you very much.
Thank you.